Hello everyone. Today is the 29th day of Leetcode 75 challenge. Let's begin with the 29th question. Question 2095. Delete the middle node of a linked list. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. Okay. So you're given a head of a linked list. Fine, let this be the head. Okay. The task is to delete the middle node from the linked list. The middle node is defined as the node at index n by 2 using zero-based indexing, where n is the total number of nodes in the linked list. So what they're trying to say, let this be a linked list and let this be the zero-based indexing for each node. So here n is 4, number of nodes are 4. We divide it by 2, we get 2 as the output, right? So according to them, the n divided by 2 is the middle node here. So this will be the middle node, fine. So we have to remove this node and then our linked list will look something like this. And the linked list should remain connected and valid after the middle node. So when you remove the middle node, it should get connected again, right? It's not like that if we have removed the middle node and then we are returning a linked list of this way, right? It should be connected, right? What are the constraint? The number of nodes in the linked list is from 1 to 10 to the power 5. And the value of the node is also 1 to 10 to the power 5. I hope you understood the problem explanation. Now let's move to the next slide. Now let us understand the input-output explanation. So here you have been given 2 and 1. Okay, let this be 2 and let this be 1. Fine. I'm marking this as the indexes as per the question. So output is 2. Why? Because total number of nodes are 2 here, and when we divide it by 2, we get 1, right? So this is the 1th index node. So we remove this. So we are left with 2 at the end. Fine. Similarly, if you see here 1, then 2, then we have 3, then we have 4. Great. That marks the indexes also. Now, okay, now there are 4 nodes. So 4 divided by 2 gives me 2. Fine. Here 2 is this. So you have to remove this node, right? After removing this node, we are left with 1, 2, and 4, right? So this is the output as I said you. So I hope you understood this input output explanation. Now let's move to the next slide. To understand what problem is basically asking, we should build up an intuition to the problem, right? So let's start by understanding the goal. So we are given a single linked list and need to remove its middle node. Fine. Let me, draw a linked list here. Let me draw it in circular way. It will be faster that way. Okay. So this is suppose this is a single linked list given to us, right? And we have to remove the middle node. So here, if we see 0, 1, 2, 3, 4, and we have 5 nodes here, right? So 5 divided by 2 gives me what? 2.5, but in integer format it will be 2, right? So this node will be removed. So the middle node is defined as the node at index n by 2, right? Zero-based indexing. Now, since we cannot access nodes by indexing directly in the linked list, like in an array, if you get the index value, you could directly just write array of index and get out that value, right? But in linked list, you cannot do that, right? We need a way to reach the middle efficiently without counting all nodes manually. This I will tell you what is this. But in linked list, you cannot just do like linked list and you wrote the node here and it's just that you get the value of the node. That is not possible in a linked list, right? You have to just move ahead in a straight line. So one way which could come to our mind is okay, what if they are saying that n by 2 is the middle node. So what if we do an iteration, we do a for loop in the linked list and we get the number of nodes, which is in this case is 5, right? If you get this and I divide this and get the value as 2, and I only iterate the half of the linked list, I could reach the middle point. And after that, what I will remove these connectivities from here, and I will try to connect this from this node to this node, right? So that the we have the total connectivity for the linked list, right? As I written here, one way could be count the nodes and divide the number of nodes by 2, right? The index which we get, we can iterate till there, and you get the middle node here, right? So this is the thing which could be done, but yeah, but this is a kind of an inefficient solution. Reason being, you are iterating one time for finding the length, fine. Then again you are iterating n by 2 times, n by 2 length, right? After that, then you do the connectivity. Yeah, the solution will be correct, and it's not a wrong approach, but it is a time consuming one. So let's look for the another approach and build up our visualization process for it, right? Now let's go for the visualization process. Let me draw the linked list again. This is great, I think. Okay, fine. Imagine 2 pointers. Fine. One moves one step at a time. Let this be a one pointer, right? P1, and other pointer moves 2 steps at a time. Let this be the 2 pointer. So this pointer moves one step at a time, and this pointer moves 2 steps at a time. Fine. Now, as fast reaches the end of the list, fast means we could say this as the pointer 2. Let this be fast, right? This be a pointer 2, and this pointer 1, let it be slow pointer. I'm naming that name as fast and slow. Fine. So as fast pointer reaches the end of the list here, the slow ends up exactly in the middle. Now, how, right? That's the question which you are getting. Let me tell you how. Let this be the F means fast, S means slow, right? Slow came here in first iteration, fast went here in the first iteration, great. Then fast went in. Let me clear up some extra lines here. This one, this one. Okay, I will remove this S also, fine, and I will remove this S. Now this S comes from here to here, right? S is standing here right now, and F or the fast pointer moves from here to the last index. So what you can see that S is standing in the middle index of the given linked list. Fine. So this helps us to locate the middle node in a single traversal and saving the time and space both. So we are saving the space also. If you're thinking of, or if you have thought of using any data structure such as array to store the values, or set, whatever you have thought, so you have saved this space also, right? And the iterations which you will do multiple times, you have saved that also, right? But to remove the middle node, we also need to remember the node just before it, right? Now there is an issue here, like, okay, you reached here, this is a midpoint, right? Now you removed it. Let me remove the node. Okay. Now what? There is no connectivity between these two nodes, right? You have to do this. How you will do this? What if you carry another node here? Let it be previous node, which keeps the track of the just the previous adjacent node to the slope. Great. So if this is connected in this way, what we can do is that we can just tell this S node that with the help of this previous node, we can just connect this node with this node, right? So we keep a previous pointer behind slope. Fine. So this is a process which could be done. Okay. Now how we can simulate this, right? Let me draw the linked list again here. Another linked list. Okay. Okay. Now let's iterate the slow and fast pointer again, right? Slow comes here, fast moves still here, right? Then slow comes here, fast moves in the end. Okay, slow fast is done. We got the middle pointer here. This is the middle, as you can see. Fine. Now in each iteration, we move slow and one step and fast 2 step with this. Fine. Now what? As I said, we will also have previous pointer with us, right? Now previous is here, and let's point previous to none beforehand. Okay. Now when S from here moves here, previous comes here, right? When S moves from here to the middle node or the next node, previous cuts from here and comes to the node just before the slow pointer. Fine. Now what you can do? You can remove this. Let's remove this. Very simple thing. Just think that, okay, you are standing here. You said, since we don't need this node, I will remove this pointer from here. Okay, but there is no connectivity. So you will miss the opportunity to connect the previous pointer to the next node of the middle node. Fine. So what you will do, instead of removing the pointing arrow from the slow pointer, you will first try to connect this previous node with the slow's next pointer. Basically, previous next. N means next. Okay. Let me write it again. So what you will try to do, you will try to write previous next will be equals to slow next. Fine. So this we created this part, right? Now slows next. Now we can remove the next pointer, right? Slows next this bit. Now when we pointed previous to the slows next, so this is no more there, right? And we will point slows next to none. So this helps in removing this node, and we have successfully removed the node from middle node, and we got a linked list, connected linked list without any fault connectivity, right? So this is the thing which we can do when we are in the middle node. So we deleted a node by skipping it, right? Basically, we are skipping the node in that case, right? So I hope you understood till now what we are doing here, right? So now let's move to the next slide. What we figured out. Now, first we should know about the fast and slow pointer concept, right? I know many of the people might not know who are new to the linked list topic what slow pointer or what fast pointer is there. So they try to use any kind of data structures like array, stack, stat, whatever it comes to their mind, increasing space complexity to n, right? And also, if they don't use any data, say data structure or any kind of data structure, they try to use O of n to count the nodes, then O of n by 2 to, or it could be O of n also, right, in worst case, right? Iterating two times. So first, we should know the concept of slow pointer and fast pointer, right? So having the concept of slow and fast pointer help us efficiently find the middle node, as I showed you right now. The previous pointer, we should just keep in mind the previous pointer help us to keep the track of the node before the slow pointer. So we can easily remove the middle node by adjusting the link. So in many of the linked list question, you will find using previous pointer, right? With some other pointer or slow pointer most of the time. Because we have to keep track, right? What was the previous node before slow, so that if this slow is removed, and you have to connect previous with the next node. In that case, the previous pointer is the most more comes in handy. So this is all about the intuition. I hope you understood how the intuition is working. So now let's move to the next slide. Before going to the approach, let's understand what is fast and slow pointer in much more detail, right? So slow and fast pointer are also called tortoise and hare algorithms. Okay, it is a simple yet powerful technique used to solve problems in linked list by moving two pointers at different speeds. Now, mainly originated from mathematics, specifically from cycle detection algorithms. Okay, keep in mind. Let me cycle detection algorithm, and it was created by Robert W. Floyd, who also wrote the algorithm Floyd-Warshall algorithm. Right now, this technique helps in tasks like detecting a cycle, finding the middle element, and solving other problems efficiently without any extra memory usage. Fine, and how it works? We initialize two pointers. One is fast pointer, and another is the slow pointer. Right? Fast pointer moves two steps. Slow pointer moves one step. Fine, and at a point, if it is a circular linked list, so there will be a point where both will meet each other. Okay, and if it is a singly without a circular linked list, the slow pointer will be in the middle node when the fast pointer reaches the end, right? That's why I wrote here analyze their behavior when they meet or when they reaches the end. Fine. And why it is efficient? It allows you to solve the problem without extra memory or nested loops and works in O of n without O of 1 space complexity. Now, it is ideal for detecting cycles, finding middle elements, and okay, without needing any extra passes. Now, where fast and slow pointer is used? Okay, I have taken some of the examples where it is used. So, it is used in cycle detection in English, detecting a loop if it is exist, finding the starting node of the loop, right? Like if it is a loop. So, okay, you have detected the loop using the slow and fast pointer, but what was the value? So, using this slow and fast pointer concept, you can find the value also. Now, find the middle element of the linked list. This is the this is the linked list. So, finding the middle element also is done using the slow and fast pointer. Now, removing the nth node from the end by keeping a gap between the pointers. Okay, check if linked list is a palindrome by comparing nodes from both ends. So these are the few of the examples, or you can see example only where the fast and slow pointer can be come in handy. I hope you understood the concept of slow and fast pointer. It's not that much of a hard thing to understand. Okay, now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. Fine. First, we will start by handling the base case. Check if the linked list is empty or has one node. For example, if there is no linked list present, right, you will not be able to find any middle node, right? Okay. But what if there is only one node? If there is only one node, this is only the middle node for that linked list, right? We will just return the head for it. Fine. So if yes, we return no, none, because there is no middle node, right? If there is no middle node, what we cannot return? Nothing, right? If there is only one element or one node, it is not a middle node, right? So we will return none. Okay, because if we delete this node, there won't be anything, right? That's why. And if the link, if there is no linked list present, then also we will return none. So why we do this? Because to ensure we don't perform unnecessary operations or run into errors when the list is too short, right? This is the basically precautions which we take while writing the base case. Now, second step will be initializing the pointers. We create three pointers: slow pointer, fast pointers, as I explained why, and both starting at the head of the linked list. Now, I talked about previous pointer also, just and we initialize it to none because we will follow the slow pointer eventually. Fine. And why we do this? Because slow help us to reach the middle node. Fine. Fast moves faster to end and the end to end. The fast moves faster to end the loop sooner, and the previous used to track the node before slow for deletion of the middle node. Fine. If you remember, I just showed you in the intuition part that if previous is standing here, slow is standing here. If I remove this slow pointer node, I have to connect this previous pointer node to the next pointer of the slow pointer node, right? So for that, we need the previous pointer. And third step, we try to find the middle node. We traverse the list using a while loop. A while loop goes till we try to iterate the fast pointer when till time it is not none, or fast dot next is not none. Fine. Okay. Till that time, we iterate the linked list to in the way like slow goes slow dot next one step, fast goes fast dot next, and previous pointer is here, right? So previous pointer stores the slow pointer, then we move the slow pointer ahead, then we move the fast pointer ahead. Okay. This is what I have written here. And why we do this? When fast reaches the end, slow will be in the middle again and do the difference in the speed. Fine. Now we delete. Now the step 4 is deleting the middle node. Now once the loop ends, slow points to the middle node, right? Let me draw a place for the visualization process. So for example, fast is standing here and slow is standing here, right? And previous is standing here. So we use previous dot next equals to slow dot next to skip over the middle node, right? And previous, as I showed, previous dot next will be equals to slow dot next, right? So this will point here, and slow dot next becomes none, right? So this gets removed, right? And we have the linked list ready without the middle node. And this safely removes the middle node without affecting the rest of the list, right? Yeah, I have written here optionally set slow to next none to fully disconnect the middle node, because if we don't do this, the middle node will still be here and it will be a garbage collection for us, right? So we don't want that. We have to remove this complete node, correct? And at the end, we return the updated head. We return the head. After deletion, return the head of the modified linked list, because the function must return the updated list with the middle node, right? Since the slow pointers points to the head node only, right? And fast also. So when we update slow or fast pointers, we are basically updating the main head pointer, right? So that's why at the end we return head pointer itself. Fine. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Okay. Now let's understand it line by line. So as I said, if head is null or if head dot next is null, we will return null because middle pointer is not possible there. Then we take the pointer, slow pointer, fast pointer, and previous pointer. We point slow to head, fast to head, and previous to none. Initially, now we do the while loop while fast is not none and fast dot next is also not none, and we keep on updating the pointers. Previous comes to the slow pointer, or slow like whenever. Let me draw it here only. If slow is here, previous is here. When slow moves, before slow moves to the next part, previous comes here, then slow moves here. Fine. That is what's happening here in these two parts. And yeah, fast is going two steps at each time. So fast dot next. And when this complete iteration is done, we just we point the previous next pointer to the slow's next pointer. and slow's next pointer is pointed to none, and we return the head. So the time complexity which we take in this is O of n because we only iterate one time and in one pass, okay, and there is no extra space used here, right? So I hope you understood this code explanation. Now let's move to the next slide. Now since we have the understanding of the code, let's look at the dry run of the example. Fine, draw it here. Let it be some big 3, and we have 4, then we have 7, then we have 1 here, then 2, then 6. Great. Let me mark their indexes also 0, 1, 2, 3, 4, 5, 6. Great. Now, S with the slow pointer, F with the fast pointer, please keep in mind, P with the previous pointer, right? This is F. And this points to none, this points to head, which is given to us. This also points to head, which is given to us. Fast is here, and slow is here, fine. And previous is pointing somewhere in the none. Okay. Now in first iteration, we were saying that while fast is not null and fast dot next is not null, right? We could see that fast is not null, fine, and fast dot next is also not null. Let me write the condition here. Fast is not null. I'm writing this way, fine, and fast dot next is not null, fine. Here also the same thing. So fast is not null and fast dot next is also not null. So we move. So what we did, we just put previous here, slow here, and fast here. Correct? Again, we can see that fast is not null and fast dot next is also not null, right? So we put previous here, slow here. We write it properly. Slow here, and fast will move 2 steps ahead. Okay, we'll remove this now. We are done with this. Great. Now fast is not null. Okay, and fast dot next is also not null. So fast moves from here to the last node. Also, slow move previous moves to the slow pointer's place, and slow pointer moves ahead in the middle part, right? Now we'll remove P also, slow pointer from here, fast from here. Great. Now we can see that fast is not none, but fast dot next is none, right? So we come out of the loop, and what we did there, if you remember, I wrote there previous dot next is equals to slow dot next, and slow dot next equals to none. Fine. So if we just follow the steps which I wrote here, previous dot next points to the slows dot next. Slows dot next points to some value none here. Fine. So I will remove this pointer from here 10. Okay, and this gets removed. Right. So finally we could see that this middle node is detached from the linked list, and we return the head. And when we return the head, we get output as 1, 3, 4. Then again there was 1, and there was 2, then there was 6, right? I will just join them. Yeah, this is our resultant array, resultant linked list. Sorry. Does it match with our output? We get 1, 3, 4, 1, 2, 6, 1, 3, 4, 1, 2, 6. Okay. So we have successfully did the dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition and also the slow fast pointer concept, then the approach, and then the code. After that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Okay, now let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the lead code and code the solution. Okay, now let me code if head is equals to none or head dot next equals to none, we return none, right? So there is no middle node possible here. Then I will initialize pointer, slow pointer, fast pointer, then previous pointer pointing to none, not this fast pointer, we point to head itself. While fast is not none and fast dot next is not none. Previous will take the place of slow pointer. Slow will move to slow dot next. And first, of course, will dive into two steps. That is done. And we will remove the middle pointer, middle node by writing previous dot next equals to slow dot next, and slow dot next will point to none, and we will return the head at the end. Fine. Now let's submit the solution. See, okay, we have written by mistakenly outside. Okay. Now let me run again. Okay, we have successfully accepted for this. Now let's submit the solution. Great. We have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find a link in the description. Thank you, everyone.